bring even the most well-architected data pipelines to a grinding halt. It's this silent, creeping issue that causes slowdowns, instability, and just endless headaches for anyone working with Kafka.
You've probably been there, right? Your producers are sending data like crazy, your brokers look okay on the surface, but everything downstream is just lagging. Messages are piling up, latency is through the roof, and for the life of you, you can't figure out where the bottleneck is. It feels like you're stuck in some kind of invisible data traffic jam.
Well, that traffic jam has a name, and the culprit is very often this silent killer called backpressure. Today, we're not just going to talk about it, we're going to diagnose it, we're going to fix it, and we're going to look at how to build systems that are pretty much immune to it.
Okay, so first things first, let's really get our heads around this. What exactly is this invisible force that's wreaking so much havoc on our systems?
You know, the simplest way to think about it is this. Backpressure is what happens when you're trying to pour water into a funnel way faster than it can drain out the other side. Your producers are sending messages at a blistering pace, but your consumers, or maybe the database they're writing to, just can't keep up. This imbalance creates a system-wide bottleneck, that massive data traffic jam we were talking about. And the impact? Oh, it's devastating. It's a chain reaction. Producers start getting timeout exceptions and failing. On the other end, consumers fall further and further behind, which leads to massive lag. This can trigger what's called a rebalancing storm, where your consumers get so confused they just keep joining and leaving the group, which halts all processing. And at the system level, your poor brokers get overloaded, their disks start thrashing, and the entire Kafka cluster can become unstable. It's a mess.
So how do we fight back? The good news is we have a lot of tools in our toolbox. And your first line of defense is right where the code lives, in your producers and consumers.
On the producer side, we've basically got two main levers to pull. First, we can throttle the rate directly, literally just tell our application to slow down a bit. Or, second, we can get smarter about how we batch messages. Instead of sending these huge, overwhelming clumps of data, we can send smaller chunks more frequently. This creates a much smoother, more manageable flow of traffic for the brokers to handle. And the great thing here is you can do this with just a few simple configuration changes. You can decrease your batch size, you can set linger MS to 0 so messages are sent right away, and you can enable compression to shrink the data before it even hits the network. You can even adjust your AX setting. If you're willing to trade a little bit of durability for more speed, setting it to 1 can really help.
Okay, now for the other side of the equation. We have to help our consumers keep up with the flow. We can scale horizontally, which is just a fancy way of saying add more consumers. This lets them process topic partitions in parallel. Or we can scale vertically, which means making each individual consumer more powerful, maybe by using multi-threading to process multiple messages at the same time.
And just like with producers, we have some key configs we can tune. Increasing max.poll.records lets a consumer grab a bigger chunk of work in one go. Lowering fetch.min.bytes makes sure it's always ready to grab new data, even if it's just a small amount. And this one is huge, setting enable.autocommit to false. This gives you precise, manual control over when a message is truly considered done, which is crucial for building reliable systems.
But what if tuning your applications isn't enough? You know, sometimes the problem is simpler. Sometimes you just need bigger pipes. And that means we need to look at the Kafka infrastructure itself, the brokers and the topics.
Strengthening your infrastructure usually follows a pretty logical path. Step 1, increase the partitions in your topic. This is the absolute key to unlocking more consumer parallelism. If that's not enough, then step 2 is to add more brokers to the cluster to spread the load across more machines. And of course, step 3 is making sure each individual broker is a real workhorse with plenty of CPU, memory, and fast disk I/O.
But it's not just about adding more hardware. You can optimize what you already have. Enabling log compression on your topics can drastically reduce how much disk space and network traffic you're using. But honestly, the most crucial thing here is that you have to be watching. Actively monitoring your cluster's health is completely non-negotiable.
Because at the end of the day, you absolutely cannot fix what you cannot see. Using tools like Prometheus and Grafana to build dashboards for your key metrics, this isn't some luxury, it's essential. It's how you spot bottlenecks before they turn into catastrophic failures.
So far, we've talked a lot about reacting to backpressure after it happens, but now let's shift gears and talk about something more advanced, building systems that are inherently designed to handle it from the start, systems that can actually push back.
And this quote right here perfectly illustrates this next evolution in system design. Modern reactive frameworks, like Project Reactor for Java, are built from the ground up to handle streams of data. They have non-blocking backpressure built right in. This isn't about you manually tuning configs anymore. It's about building a system that can dynamically adapt to the load all on its own. This brings us to a really powerful concept called flow control. Imagine if your consumer could literally tell its producer, hey, I'm totally swamped right now, can you please slow down for a second? Well, that's flow control. It's this dynamic, almost conversational approach where systems signal their capacity to each other, allowing the whole pipeline to adjust its speed in real time.
So here's how it works in practice. A database starts getting overloaded and sends out an overload signal. The Kafka consumer gets that signal and just stops polling for new messages. It just waits. Then, once the database catches up and signals that it's ready for more, the consumer automatically resumes fetching data. It's this beautiful, elegant, self-regulating loop.
And there are a couple of other patterns that are absolutely essential for resilience. A bounded queue acts like a shock absorber inside your consumer, smoothing out any sudden bursts of messages. And a dead letter queue, or a DLQ, is your safety net. It prevents a single poison pill message, one that just keeps failing, from blocking your entire pipeline. It just shunts that bad message aside so you can look at it later.
So let's bring it all together. Solving backpressure isn't about finding one single silver bullet. It's a holistic approach, right? It's about optimizing your producers, scaling your consumers, strengthening your infrastructure, and ultimately adopting these resilient design patterns that can handle the unpredictable nature of real-world data flow.
Which really leaves us with one final important question to think about. It's pretty easy to build a system that's fast when all the conditions are perfect. But the real challenge, the real mark of a well-designed system, is building one that is truly resilient, one that can bend without breaking when it's under pressure. Because in the world of data, pressure isn't the exception, it's the rule.